Hello everyone, my name is Rebecca Moussa. I'm a PhD student in the Solar Group at the Crest Center at University College London. In this talk, I'll be presenting our work titled Learning from Mistakes, Machine Learning Enhanced Human Expert Effort Estimates, published in the IEEE Transactions on Software Engineering journal. This is a collaborative work with Professors Sarro and Harman and Dr. Petrozziello. As you may know, it's only normal and a part of human nature to make mistakes, and then, hopefully, learn from them. As kids, almost everything we do falls under the learning experience. Some of them are trivial and straightforward, like touching fire, getting burnt, and then learning that fire is associated with harm and physical pain. But as we grow older, we learn that some of these tasks are in fact a bit more complicated and require more than just memory and repeated failure to learn from. For intricate tasks like these, one life might not be sufficient for one to commit and learn from all possible mistakes. Now, if I were to ask you about the weight of this bottle of sand, you can probably give a random guess. Chances are, without any prior knowledge, this guess is going to be, well, off. First mistake, but that's okay, because that's how we learn. I'll then give you the true weight, add a bit more sand, maybe drop a pebble or two in that bottle, and then ask about the weight again. Realistically, without knowing the weight of the pebbles or the amount of sand added, well, there goes mistake number 2. I can keep going on about this, but I believe you all get the point. Lessons from mistakes like these are not as straightforward, and one's own mistakes solely might not be enough. So what if I tell you that based on the mistakes you and others have committed, I can predict the error of your next estimation and help you adjust it for it to become more accurate? Well, this is the core idea behind our work, dubbed as LFM. It's a novel approach which exploits and predicts characteristics of the error resulting from humans and uses them to learn, adjust, and enhance the performance of software engineering tasks. Now, when the estimation is more significant than the weight of sand and pebbles in a bottle, and is in fact about the effort required to develop or complete a project, one can understand why these misestimates can be damaging to a company, and why this task is a crucial activity for project planning and monitoring, specifically for ensuring that the product is delivered on time and within budget. So we apply LFM in the context of software development effort estimation, where in order to support engineers in obtaining more accurate estimates, researchers and practitioners have attempted to devise various automated methods over the last 3 decades. But despite the rise of automated modeling and its application to software effort estimation, human expert judgment is still the most commonly applied estimation strategy for software projects. However, existing surveys on estimation practice suggest that human effort estimates tend to be over-optimistic, and that there tends to be overconfidence in their accuracy. Now, a lot of work had been done on the phenomenon of overconfidence and underconfidence and on the uncertainty of human expert estimates. Experts are humans, and as I've said, we all make mistakes. That's inevitable. This observation motivates us to depart from received wisdom and current research practice in the predictive modeling community. In this work, we shift the focus from creating automated models able to predict software effort to creating automated models able to predict the errors made by human experts when estimating effort and using this to adjust their estimates. Rather than seeking solely to compete with or even replace human experts, our approach learns not only from traditional past projects, but also from past expert judgments, essentially building into the predictive model the ability to learn from their past estimation errors. So starting from past software projects, where several cost drivers, such as the estimated size of the software, for example, or information about the team, are taken into consideration at the time of the estimation, and for which expert estimates of effort and actual effort recordings are available, our approach computes 3 types of misestimate characteristics. These are namely misestimation type, so whether the expert had under or overestimated, the misestimation severity, divided into 3 categories, low, medium, and high, and the misestimation magnitude. The approach exploits this gathered information in order to find similarities between a new target project and past projects. It uses this knowledge in order to predict the characteristics of estimate error for the new target project, and then uses it to adjust the final estimates. The early identification of potential under or overestimates and their severity can better guide human experts in understanding their predictions. On the other hand, the predicted misestimation magnitude can be used to automatically adjust the human expert estimate of the target project as shown in our work. Now, in order to verify the feasibility and effectiveness of our approach, we carried out a thorough empirical study which investigates the use of 5 widely known machine learning techniques on a total of 402 industrial software projects spanning across different domains and sources. We follow the most recent best practice for the evaluation of prediction models in software engineering, which includes the use of robust evaluation measures and statistical significant tests. You can find more details in the paper. So we first investigate whether the characteristics of the error are indeed predictable by verifying the extent to which the type and the severity of human misestimates can be accurately classified. The results of our experiments reveal that we can in fact classify the misestimation type with a high accuracy, represented by an average AUC value of 0.71 across all techniques and datasets, as well as being able to accurately predict the misestimation severity with an AUC of 0.70. This shows that LFM can provide software engineers with a warning regarding whether they might be under or overestimating and the extent to which they are doing that. We also verify whether LFM is capable of accurately quantifying the magnitude of the error committed by human experts when estimating software effort. The results reveal that this is indeed predictable with high accuracy as shown by a low median absolute error of 0.28 on average across all techniques and datasets. Therefore, this information can be used to adjust and possibly improve the final estimates. To verify this, we investigate whether the adjusted estimates provided by LFM are more accurate than those provided by random guessing, by traditional machine learning techniques, and by human experts. Benchmarking the final adjusted estimates provided by our approach against random guessing and traditional machine learning techniques revealed that the performance of LFM is always statistically significantly better than random guessing. LFM also obtains lower absolute error values than the traditional machine learners on 21 out of the 24 cases, with a statistical significant difference on 20 of them, which is approximately 95% of the cases. Our results also show that LFM enhances human expert estimates on all datasets, with results on 4 of 6 of the datasets being statistically significantly better than the original human expert estimates. So, when it comes to applying our approach in practice, one can follow these 3 simple steps. One should first maintain a database of projects, for which both the effort estimated and the one actually needed to realize the project have been recorded, together with the cost drivers characterizing the project. Then, for any new target project, use LFM to classify the type and severity of the errors human experts are likely to make when estimating the effort needed for target projects based on the information stored in the database. Maybe raise the alarm that the expert might be under or overestimating with a low, medium, or high severity. Then use LFM to quantify the estimate error for target projects based on the magnitude of human expert past misestimations. Then finally, adjust and enhance the human expert effort estimates based on past errors learned from step 2. Now, going back to that bottle of sand and pebbles, in case you were still wondering, I would estimate its weight is slightly lighter than 2 times log base 7 of 65 over radical 46 plus 1. Or, in other words, around 3.32 kilograms. But then again, what do I know? This might be yet another mistake. Thank you for taking the time to watch this.